Hey, we're working. All right. So, hello everybody. Oh, we don't have our screen on. This is a sec to warm up here. So, unfortunately, we were not able to do the MRI today because a delay in getting the liquid nitrogen to be able to cool the MRI. So, Dr. Olafson, Physics Olafson, not ECE Olafson, made the request for it, and they, since the last time he ordered liquid nitrogen, they added several more sign-offs in order to access it. So all for safety, which consequently added an extra day or two. So he'll be able to get like tomorrow, but that's not good enough for us. So on Thursday, we'll be over there because that process is already gone. So what I wanted to do today was to talk over one of the topics from the project you're going to be building. As I mentioned, we're going to build discrete optical tomography. We're going to do this using cell phones, basically. So we need a system that's going to basically rotate and have a something like a laser in the red spectrum that's going to run through it, and you're going to record video on it. And then you'll be able to take individual slices of your videos and group together the pixels, because your camera is going to be way higher resolution than we will probably be able to easily calculate on MATLAB. You could, in theory, use the higher resolution, but you'll probably just bog down in horribly bad ways. So, but we'll discretize it and everything else. Essentially, it's going to look exactly the same as the X-ray. That's why I haven't worried too much about it. I'll give you a couple papers, actually a chapter or two from a book on this that I have, and you can kind of look over it to see the background to it. It's going to, like the book did, go through all the gory integrals, but you'll notice the integrals look exactly like what we did before, right? Just like for the radon transform, there's going to be an integral that's going to sum up a whole bunch of, scattering and extinguishment coefficients, essentially, that will be used to give us our curved path and absorbed light pattern. So essentially, it's going to be the same as that, just we're not going to have straight paths. We'll have a slightly different path to it, but we'll still be able to, use the basic idea of it. So, but I'll give you that. I'll upload. I have to cut it out of the PDF to make it fair use size, and then I will share it on the class canvas. So if you could just look it over briefly so you kind of feel familiar with the ideas. We'll talk a little bit more about it after the break. Because essentially after the break, the only thing we're doing is working on the project. Most of it should be fairly straightforward, a conversion of what you did for the CT. So we just need to build the base system, which is what we're going to be talking about today. How do we actually do that? And then you'll just have to take measurements, change your, import your video, downgrade the size a little bit, and then we'll use that to do our scanning. We'll probably just grab a single row to do a slice for simplicity's sake. But anyway, that'll give you kind of a basic rundown of what we need to do. Now, when I was looking at doing this, we have to rotate a sample. So what do all of you think is the easiest way to rotate a sample? Okay. Let's say something small enough that light's going to pass through it, semi-diffuse, so imagine you're talking a few inches. Yeah, somewhere in that zone.
Have a platform for it, have that platform have a coupling to a motor, servo motor.
So we need a motor or a servo, something lightweight to rotate, and we need it to move at a constant speed. How can we get it to move? Like if I had a servo, how can I get a servo to move at a constant speed?
By just stepping it at a constant speed.
Okay. Right, so what can I do to make that happen? So that might be, so that'll be a good one. I'll talk about servos and say, has anybody else used servos? One person. So the rest of you have never used a servo, correct? Yes. Okay, let's take a second to talk about servos then. So a servo is basically a motor, but it's a motor with a controlled input. So you can tell it, depending on how you set it, there's two varieties to them. You can either tell them a speed to rotate at or a position to go to. Right? It'll depend on how you set up the internal servo. And if you think about it, this is basically a simple control differentiation, right? Because position and rate are just derivatives. So it's which input are you handling? So it's a minor modification of the servo controller to get a rate servo or a position servo. Typical servos, that control signal, I want a single wire to specify this. So we're going to give 3 signals to it. We need a power and a ground. Typically, this is somewhere in the 6 to 7 volt range to drive most little servo motors. And then I have a single wire to tell it either where to go to or what speed to rotate at. That make sense? Okay. Now, the question is, how do I specify that? So standard servo, do you remember how it goes? What the signal is?
Not really.
Pulse width modulation, right? So we're going to send our area, right? If it's a very low duty cycle, it's going to go in reverse for rate. High duty cycle, it's going to go forward and past the 50% point. Essentially, will get you fast, slows, things of that sort. Similar for position. Basically, you're encoding a number in that pulse, and it'll just go to a certain position and then hold. So depending on which one. So that's essentially what you've got for each of these when you're going in. We've got a simple one here that's a position encoder, because that's the standard. If you do nothing else, your servo is a position servo. It's got a limit of just over 180 degrees, and those are split up typically into 255 positions, because that's what's encoded by your duty cycle. Okay. Now, given that, actually, just a side note, if you want to, there's a simple thing you can go in and pull out if you open the case up and pull it, that'll allow it to do a full cycle. And the second you do that, it's usually designed when you pull that it'll switch to a rate version. So it's usually a fairly simple way to convert them over. So now they're a continuous cycle, right? Because there's no stopper pegs to them. And that allows you to then rotate, and now it's a speed dependent setting to it. But anyway, that's a typical servos, right? Since I just asked for a servo this morning when I found out we weren't going to get the liquid nitrogen in time, I'm like, okay, I got to build this fast. I just asked, and ideally I would have actually asked for a rate one, but I didn't have time to disassemble it and reconfigure. So I just did a position, and all I have to do is set it to go to one extreme or the other, and that'll give me a forward back. So it's an easy enough one to do. Okay, now I need to therefore send one of 2 different pulse width modulated signals. Go to this end, go to that end. Make sense? Okay, so let me ask you a question then. How would you send a pulse width modulated signal?
I mean, physically, you could use a dial.
Okay.
Hook it up to a dial.
So how can I hook it up to a dial and get a signal?
I mean, the dial's going to have output leads, right? With it, if you put power into it.
So that depends on the type of dial you have, right? So the dial itself, it's going to, there are some dials that are hooked up to essentially potentiometers, right? A dialable resistance. Some are hooked up to a variable capacitors, varicaps that are on it. There are some that are position encoded ones. But if it's a position encoded one, it basically is a switch with one of several switches. All that's going to do is provide electrical connectivity. You have to, on each one of those position switches, you have to have different pulse width modulated signals of the appropriate duty cycle, basically, to be able to have them switch between them. So that's a possibility, right? I could switch between several different ones, but I'd have to have those from somewhere else, right? So how can I even build a pulse width modulated signal? Has anybody built them in the past?
Yeah, I don't
So believe it or not, we usually have you do this in digital logic, briefly, right? And then it'll depend on courses you take. So one way you could do it is I could get like an Arduino or a Raspberry Pi or a BeagleBone Black or whatever, some either microcomputer or microcontroller. And I could use their outputs. Many of them have PWM outputs built in. But if not, you can just kind of set them high, have a counter, set them low, do a counter, and off you go. So that would be one way. That's kind of a heavy system, right? Because you have to have a microcontrollers or microcomputers, even bigger like a Pi, requires a bunch of peripherals. They're fairly big boards. That's not a small elegant solution. On a kind of more customizable set, but also fairly big, I could take an FPGA, and I could actually, this is similar to what we basically do inside of digital logic. We just program one that's doing a digital counting, in essence. And I can, I count from, 0 to 255, and at a certain number, right? So I turn it on at, say, 0, and I turn it off at some number that you set, and it counts all the way. Therefore, whatever the number you set will set the duty cycle. So that's another straightforward way that I can do it. But again, it's fairly big having that. What I want to teach you is probably one of the most important standard parts that nobody ever talks about in an undergrad engineering degree. What's called a 555 timer. Anybody ever heard of a 555? It's a crazy cool device that's been around almost as long as I've been alive. I think it's only 2 years younger than me. It was designed basically to make a lot of really cool circuits. There's a market of these. They sell at least $1 billion a year. So when I say it is a pretty major component in the world of engineering, it's gigantic. Almost every kid's toy out there uses a 555 timer. Those little does certain things, whatever. It's a very common system to actually debounce circuits when you have signals coming in from a noisy source. Typically, although we show you lots of other ways to do it, almost always it goes through a 555. It's a really cheap, easy, very robust way to handle it. It's one way to make a timer, and you can accurately count up to about 5-10 minutes without having to build just on one timer. It does all kinds of cool things. You can generate clock signals. You can have just straight, if you've ever seen buttons where you just push it on and it runs for a period of time and turns off, you can easily set that up inside of a 555 timer. They just do all kinds of things. You can make a smooth, clean on-off button inside them. You can make pulse modulated signals. You can make all kinds of different modulated systems, right? Position modulated, go down the line. It's hugely popular. If you go out into the hobbyist area, it's one of the favorite hobbyist ones because if you understand basically what it does, it's almost infinitely reconfigurable, much like an op-amp, by some outside. Add a couple resistors and capacitors, and you can make it a completely new circuit. So much like an op-amp, it's kind of to timers what op-amps were to amplifiers. So it's a really good system to be aware of. So it's kind of one of those cool ones, and it gives you quite a bit of street cred. For a lot of older engineers or any of the builder markets, if you actually understand what a 555 timer is and can build these circuits, you can generate a lot of simple things like this very quickly. What if you want to know if your motor works? right? It's an easy way to do that. That's kind of what we're gonna build today. And it only requires a few resistors and some wires, a couple capacitors. But it's a pretty quick, easy circuits to build. So this is why, to me, a 555 timer is worth your time and understanding them. This is what we're going to do for our base, and then we're going to use a laser LED. So a simple LED that makes cohesive light to it, that's in the red spectrum to be our light source that's on it. Then all you have to do is take this basic setup, put it on a firm base, put a box over the top of the hole, and you can stick your camera on it, and away you go. Yeah.
So, just so I follow like what we're doing, like you're using a 5-5 timer to generate a clock signal.
A pulse width modulated signal.
Pulse width, yes.
Right.
Pulse width modulated signal.
That's gonna tell the base to move either
At a certain
forward or backwards. We're gonna have two different buttons. You hold it in one, it goes in one direction. Right. There is a limit or a stop, so you have to have a reversing one, so you can go the opposite direction. But that way you can kind of hook this up and away you go. I'll have to put these buttons, right now they're on the board. I'll put them to switches on the outside, so you can close the thing up, put your camera on the outside, and then push a button to go forward or back. So, does it all make sense? All right, so the first part, what I'm going to do here is really, there's not going to be a lot of DOT, actually, there's going to be no DOT stuff. This is all 555 today, basically. Okay, so this is a 555 timer right here. It was invented by Hans Kamen-Zinn, right? He's one of the early electronics designers. He did an awful lot of standardized chips that are out there. Besides the 555, he worked on several phase lock loop chips that are out there. He worked on a lot of the early op-amp designs, things of that sort. So there was a lot of stuff he did, but his most notable one is the 555 timer. He actually kind of pushed this one pretty hard himself, because initially the company didn't want to build them. And this is kind of one of those company genius maneuvers. The engineers who were in their design thing, the other ones, were like, why do we need to build this? People can just build this out of standard components we sell. Whereas his whole point was, well, but this is easy configure, it makes their life simple. The engineers never okayed it. It actually was overruled by a marketing manager. So I mention this because sometimes your best ideas are going to be completely squashed by your peers, but you got to know when you have something. Right? And this is when making connections with other people can probably help out quite a bit. It didn't make him friends in amongst his peers, but it didn't matter. Shortly afterwards, the company ran into problems, but he has a share, or had a share, he passed away about 10 years ago. He had a share in this because he was the designer on the patent, and this is produced by just lots of companies. So his royalty share is pretty decent. So if you figure they're making $1 billion of them a year, you don't need to make an awful lot of money per chip to become a comfortable human being. But anyway, it's sometimes marketing and other people are actually your friends on here. There's the basic design of this. So the company was Synergetics, from Signals. At the time, they were a rapidly growing company. The biggest silicon manufacturer in the linear device area was Fairchild, and they were poised to be able to take over Fairchild. And then they made some stupid decisions and lost money and eventually tanked, getting bought out. And this was like their big design that ended up getting bought out. It was, first prototype was in 1971. These are the three most common modes we're going to talk about. The astable mode. All right, so this one, whenever you hear astable, what does that tell you? Let's see if we can figure out what these modes are. Not stable. So what would that suggest? If something is stable, what's it going to do? It's going to go someplace and hold. So if it's astable, it's not going to hold. So it's going to oscillate. This makes clocks. Right? It's going to flip back and forth between 0 and 1. That's all it has as outputs. It is strictly digital on its outputs, 0 or 1. Right? It's actually based around an SR flip-flop with some fancy stuff all around the SR flip-flop. You can actually see the flip-flop right in the middle driving your output. All right? Only 2 states, 0 or 1. So astable just means it's going to flip back and forth. By adjusting the timing, you get pulse width modulators, you get clocks, all kinds of other stuff. And it's going to be external stuff for these triggers and thresholds that will let you set those. How do they actually change? What would monostable suggest?
It has one state.
One state is stable. And what are my 2 states?
On off? Or is it?
Yeah, on off. Right? That's flip-flop. Right? So in this case, it will be 0, off. It's going to be stable. So you can kick it up to 1, and after a period of time, it'll decay back down to 0. This is kind of one of those nice turn it on, turn it off type things. Right? But you never know if somebody pushes the button long enough or if they do something weird. If it gets any amount of a trigger, it will turn on and it'll hold it for a period of time. This is really good for that debounce signal, single push type of a system, things of that sort, or anything where you need a controlled period of time to charge it and then it goes back to a set state until some new trigger comes in. Right? What does bistable suggest to you? Both are stable. So I have to use my 2 switching ones, trigger and threshold, to let me switch between on and off. So you got an on switch and an off switch. You boot to one and it holds, you boot to the other and it holds. So it lets you then build those in a clean, orderly fashion. Make sense? So that's, once you understand those ideas, the names tell you exactly what you want to build. Right? There are a ton of other ones that are out there. Right? For instance, a version of bistable is the Schmidt trigger inverter that's out there. Right? This is really useful for debouncing a signal where, you know, I don't want to have to say on and off and whatever else. There's just one thing to come in, and I want it to basically debounce the signal so it can't generate noisy output. It won't flip too quick. A whole bunch. I kind of got sick. Pulse width, pulse position, got sick of listing all those. There are tons of other systems that are out there that this can build. It's as long as your arm. That's all here. We're going to mainly talk about these, and I'm just going to show you this one because I think it's kind of fun and it's useful to also know how do you build just a single inverter to the whole thing. And then I'm going to have you help me to figure out, show you the circuit that I built, and you're going to help me figure out what mode I'm using. All right, so let's talk about how it's built here. This is the system. You'll notice at the top I've got ground and power, pins 1 and 8 straight across. All right. In between there are 3 resistors. Those are equal value. In the actual system, they're 5K each. There are some systems that vary that, but 5K is the original and it is the standard. This is the source of a famous urban legend, at least in the electronics world. 5K, 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 5, 5, 5. Looks really tempting, doesn't it? It's wrong, though. That's not where the name comes from. We know it's not where the name comes because there's actually an interview with the designer, and he tells us how the name got chosen. The company that he was working for, Signetics, they used all 500 numbered things. Every one of their parts was in the 500 range. That's where the first 5 came from. The phase lock loop you just worked on was 565. And the marketing guy who supported him said, you know, I've always thought if somebody named something 555, it would sell like hotcakes because it's just 555. It's fun to say. So it was actually picked by a marketing manager to be a memorable number that fit within their numbering scheme. The marketing manager had no darn idea about the internal electronics to this, so it's no connection. So you'll actually see even some very otherwise reliable good sources about how to build circuits who will authoritatively but incorrectly report the name. So just understand that's where it goes. Now, if I've got these here, what does that tell you about these voltages? Okay, and can you even identify better than that for me? Yeah, but you can tell me what exactly that stepping is, right? Yeah, it's 1/3, 2/3 of whatever VCC is. Now, that sets these two ones. Here are two comparators. So you're going to be comparing two different signals against 1/3 or 2/3 of the total voltage. Does that make sense? So that's your reference voltages, and that's where you're going to compare this. Right? Comparator plus minus, so it's going to take 1/3 the voltage and subtract the trigger. As long as this trigger voltage is less than 1/3, the result of this is positive, which means you're going to get a positive output, which means it's going to do a set. And it will set your output. Does that make sense? So it's going to transition high, the output. If your threshold, see it's on the plus? Here's your minus, you're subtracting 2/3. In order to get a positive, threshold has to be better than 2/3. In which case then you're going to get something applied to R. After that, it's an SR flip-flop. Those are your basic signals that are in. That's what the trigger starts the whole thing. Because when it's low, it'll set the output high. And threshold turns it off. Because when it gets really high, it hits reset, which sends it down to 0. Make sense? Okay. There's your basic system. Let's take a look at two more or three more things we need to take a look at. Output is fairly simple, right? The output of this, it just goes through a system to buffer this little transistor so you don't end up having a draw from here. You don't want your current running heavily through the flip-flop. So they give you a simple driver on there that'll handle things. Don't expect too much from this. My strong advice is do not expect it to supply more than about 1/3 the voltage at a reasonably small current. But it's a heck of a lot better than a flip-flop would do. And that's all it's really meant to. As a result of this output, you cannot drive any output. If you want to drive a more powerful system, you usually put into a transistor. I can't guarantee to get this very high. So my two types of transistors, NPNs and PNPs, which would be better? What do you think? They talk about the transistors and how you pick them when you go through electronics.
I took a power electronics class and we talked about it. I just don't remember which one's better for analytic versus high voltages. I know there's one that analytic.
Yes. Okay. So let's talk really quick because this is, I want you to understand basically how you set up electronics. And there are some really easy things to kind of remember. Anybody remember what an NPN looks like? They both have this type of a setup where the arrow goes. Out where? right? Well, you want to be able to recognize them when they're going in. Anybody know how to recognize where that goes? Why do we draw that one there? UP and P, so also. Well, what is that arrow meant to tell you? It's not pointing to ground. Because you can hook these in a variety of different ways. It's actually not an in-out either. What did you say?
It's a differentiator between collector and emitter.
It does do that. But, right, because you got collector emitter, right? How about for PNPs? Where's the arrow go? Goes in and where? Top or bottom? Collector emitter. So in that case, it's on the collector, right? So why the arrow in those places? The arrow tells you which leg controls the operation of the transistor. Right? The arrow is a diode. Remember, diodes have the arrow going to the wall. We just don't draw the wall, we just draw the arrow part of it. And what this tells you is, if current flows here, current flows here. If current flows here, current flows here. That's what it means. The easiest way to remember where they go. Right? And anybody know how to tell which way the arrow points? This is drawing a diode too. This is a stupid way to remember it, but I was told it as an undergrad and I've never forgot it. So even though it's not the prettiest example in the world, it is memorable. It goes in the direction you're peeing. True in every case. Yeah, it's stupid, I totally agree. It's a stupid joke from 40 years ago, but I haven't been able to forget it. And now you too are cursed, right? But it's memorable. So you can look at any one of these and instantly tell, right? And so you can write those two letters and you get the third one by, it always follows the alternate pattern, right? So now you can instantly recognize them. And you know this is the controlling one. For most of the setups that we're going to do, right, this one at the base, this is going to be standardly our control input that's coming in. It's weak, and we need to make it to basically work. Now, remember, this is probably going to, in most cases, be pretty close to VCC, and this is going to be close to ground, relative, basically, some resistor to control current, right? Typically, that resistor is over here and here, right? But otherwise, VCC and ground go in those positions. I'm not going to worry about the resistor at the moment. Right? They do always have to be there, but I'm not going to sweat them. What's the voltage drop across the diode? Yeah, it's going to vary a little bit, right? Somewhere between 0.3 and 0.7. Right? 0.3 is germanium, 0.7 is silicon. If you've got some compounded thing, it's going to be somewhere in that zone. Less than a volt, something like that. So let's say it's something less than a volt. So if this is VCC, in order to make this, right, for this to flow, this has to be less than VCC minus, let's just say 1 volt for simplicity, right? Once this is less than VCC minus 1, this opens up. To turn it off, this has to be higher than VCC minus 1. Right? That make sense? Okay, let's think about this one. This is pretty darn close to ground, because we usually want to put the resistor opposite our control. The reason is you don't want the voltage drop on the resistor adding more confusion. to where the system, where is that cutoff voltage, right? So your resistor is up here and your resistor is down here, right? Opposite control. This is ground. In order for this to turn on, what voltage does this have to be? Ground plus 1, which is going to be say 1, right? 1 or something a little less than 1. Okay. That means I have to be able to get less than 1 or bigger than 1 to control this. And let's say VCC is 5, 6 volts, whatever. Let's say 5 volts just for simplicity. I have to get less than 4 volts to turn off, more than 4 volts to turn on. Which one's going to be easier for my system output, given everything I said about how it works? Right? Not the strongest output, because almost none of our digital drivers are very strong. Which one's going to be harder to do? The PNP, because I have to get a high voltage. So as a basic rule, you cannot drive a PNP from the 555. It's usually just not allowed. If you want to drive a PNP, you have to drive an NPN and have the NPN drive the PNP. Because that you can do. So you can do a 2-stage. This is true with an awful lot of other output systems. This basically prevents you from overburdening any of your digital outputs on the chip, requiring too much power, requiring you to overheat the whole system. So this is just a safety function. Does that make sense? Okay. Now we have our output. And we know if we want to drive anything, we're going to have to use an NPN. Yay, right? Now, believe it or not, when you go to CMOS transistors, the same basic pattern of PNP, but now you have an oxide layer, makes PMOS. Same pattern over here with an oxide layer separating that instead of a current control, you have the oxide layer for a voltage control. Right? Your NPN becomes an NMOS. And they also function on, this one is said to switch ground because the resistor is not between ground. So you get a pure ground off of NPN or NMOS. Off PNP or PMOS, you're going to get a pure voltage because you put the resistance to protect it on the other side. So we say these, the P1s switch voltage and the N1s switch ground. So if you're switching power, use a P. If you're switching ground, use an N. And that way you can pick which transistor you want to do. If you're switching a lot of current, you probably want a BJT. Right? If you're switching voltage, in general, you want a CMOS. Yay. Right? There are some other reasons BJTs are less static sensitive. NMOS and PMOS are going to be faster. They're going to be overall to handle more power. They're basically usually better chips, except they are static sensitive. So, okay. Good with driving. Okay. All right. So don't just take this as for this class and this project. This is what I'm telling you is general design things you're going to want to remember for your career. Okay. So now we've talked about ground, trigger, output, VCC, and threshold. We got 3 more to go. Let's talk about reset. When you see that reset coming in, what does it tell you? Not only it's reset, that's the obvious thing, right? Brings everything back to the initial state, output 0. But what can you tell from a reset on an SR flip-flop? What things might I want to know about a reset on an SR flip-flop? Well, what if I trigger and I reset at the same time? One says turn it off, one says turn it on. It does, right? But see, that's a note they put in there. You don't actually need that note to tell you. right? The reset low, that's what the bar means coming in. Whenever that comes into an SR flip-flop, it is what is called an asynchronous input. It will switch it at any time. It is the highest priority on the system. It overrides everything. These are also set up that set overrides that to avoid the danger situations, right, with an SR where they can go metastable. So they don't draw everything in here, but there is a little circuitry. You can't assert both of them at the same time and go metastable. And they set it so S overrides R. Yay, right? So this is an asynchronous reset. Is a great way to start. You can actually use this as part of your circuit to deliberately bring you back to start in some cases. Okay. Control voltage, right? Imagine this wasn't here for a second, right? This line that it's attached to just goes right to that 2/3 point, doesn't it? So then, if I have an external access to this, what do you think that does? It overrules that voltage. So say this is 5 volts, but imagine I hook this to 5 volts. That means this is 5 volts and that's 5 volts. How much current's flowing here? Nothing. Essentially, you've removed that. And so now you've got a straight voltage divider. So I can change my voltage. I can overrule whatever's there by assigning it. Since that's a resistor, I can go higher or lower. I can switch it to what I want. So I can switch it from a 3-position to a 2-position system, bypassing that area and getting a fixed voltage here that I control from the outside. And I can even make that voltage controllable from some other source. Make sense? So this is just another, we got lots of little tweak values here, right? And that's the whole point. They're just giving you a lot of ways to get into the system to force things to go. Okay, let's consider this. What is this? The arrow tells you that this is B and that's N, so this is NPN. Right? And you can tell it's switching ground. Yay, right? So Q bar, so if this is telling me, right, if this is above 1 volt, it'll connect across here, right? And it essentially hooks this pin to ground. Right? If this is 0, it's ground, what happens? Nothing flows here, so it's disconnected. Right? So this allows me to discharge, to hook something to ground whenever Q is low. That makes Q bar high. There is a resistor to control it on here, but it's not worth drawing. Right? So this is a selective discharge. We can use that to charge and discharge external capacitors. We can use power to charge things up, and then we can, whenever this one does its state switch, right, and that goes low, this goes high, I can discharge something. So I can now use the charge and discharge of a capacitor to do timings. And this is how this gets external timings. It's all going to be RC circuits, charging and discharging. Or we just use that discharge line if we want to cut out whatever we need. That make sense? Okay, so this is your basic setup of what's on. Now, there's going to be some standard pin configurations we use on these. 8 should always be on top. Not everybody draws it this way, but everybody should draw it this way, right? So there's going to be a couple rules here. When you draw your circuits, you're going to draw a box. You're not going to draw all the internals. But 8 is always on top. 5 is pretty much always on top. Right? It can be on bottom too. I'll be careful on that one. 1 is always on bottom. without a doubt, right? And then the rest of these are gonna depend kind of where they go. 4 is usually tied high because we don't want to reset. So I should say the most common thing has 8 and 4 on top. And it has 1 and 5 because we don't always use 5. So if 5 is not being used to set a voltage to it, it's almost always on bottom end. Because then I don't want to set a voltage to this, but this is now right kind of in the middle here. Right, so I can use it, I mean, I might as well use it for something, otherwise it's an antenna. What I can use this for is for removing noise. So let me ask you, how do you remove noise? You got noise in a circuit, you want it to go away. Okay, I totally agree, right? So how do I build the world's simplest filter that I want? Do I want high pass, low pass first, I guess?
Noise is mostly.
There's noise in here, what do I want it to do? I want it to leave, right? So whatever the noise is, I want it to go out 5. Does that make sense? So where's noise? In the high or the lows? What? That's one theoretical description, but it's always compared to your signal. It's much more in one band than another. High. Because you don't have signal up there. So we say the noise you can easily identify is going to be in the high zone. So I want a high pass filter because I want the noise to pass and go out. What passes high? A capacitor. So what we're going to typically do is put a capacitor in the ground. All your high frequency noise goes right out down through that capacitor and it's done. This is almost always a 10 nanofarad capacitor. I have looked over the majority of my lifetime. I started building circuits with 555s in the 1980s, and I can just tell you, in that entire time, I don't remember ever seeing anything other than a 10 nanofarad capacitor on this, unless you're assigning a voltage. So if it's on the bottom, it has a 10 nanofarad capacitor at the ground, and it is entirely there to remove noise from this comparison area, so that you get a smooth, clean comparison. Make sense?
You said it's acting as a high pass filters to pass the high frequency.
Yeah, because you've got high and low. You want DC here, right? I mean, that's the whole purpose of this voltage divider, is to create DC values at 2/3, 1/3. Sorry, 1/3, 2/3. Dyslexia attack, right? But technically speaking, you got noise in your system, and wires pick up all kinds of junk, right? So it's technically 1/3 plus noise and 2/3 plus noise. If I hook this as a filter to ground, i.e. a capacitor there, the noise goes away and you're just left with a clean 1/3, 2/3, or a much cleaner, I should say. Nothing's perfectly clean. Make sense? Okay, I think that covers everything on here. So theoretically, at this point, you understand how a 555 works. That puts you vastly ahead of most people out there. And again, since this is a hugely popular one, big thing. Let's talk about astable mode then. All right? So basically, exactly what we said. It's now flipped between 0 and 1. It makes a square wave. It's good for pulse width modulation. Pulse width modulators are a variant of these ones. There are a few fun things we can do with them. I originally included the graph instead of a table here from the spec sheet, and then I found they actually had a very nice table inside of Wikipedia. So I thought their table was more readable than the spec sheet's graph. Surprising but true. Okay, every one of these, so you can see they've got that basic sound. 8, 4, 1, 5, 7, 6, 2 on the inputs, 3 is your output. technically speaking, 7 is an output, but it's an output that comes back into your control circuit. So we put it on the left. So this is a standard way of drawing these. You can see my little, 10th nanofarad capacitor that's in there. Nice little tiny one. This is the circuit that determines all the timings. Right? So this capacitor is one that's going to charge up and discharge. So remember, this is basically setting where my thresholds are going and everything else. And it's basically setting between turn it on, turn it off. So if you remember on our previous one, right, 2 is your trigger, 6 is your threshold, and take a look. Who's hooked together? Right? I've hooked together trigger and threshold. 7 is my discharge, which is going to be used to discharge this capacitor through this resistor. So this will set one of our 2 modes. Right? Remember, whenever my output is low, this one sets it to discharge, so that's discharging. Whenever it flips the other way around, the output goes high, that is disconnected, so VCC charges the capacitor. So the capacitor's voltage will start discharged, 0, because it had been in the low output, i.e. the discharge state. It goes high, that turns off, I start getting a trickle charge in, and this will then charge by, a time of R1 plus R2 times C. And then I care about getting basically 2 of the units up. So essentially, I've got the time that I'm going to stay at the high position when I'm doing the charging will be the sum of those 2 resistors times C. Natural log of 2 is your timing constant. But essentially, it's charging up here. This gets higher and higher voltage. When it gets above 1/3, it stops asserting send to high, but it'll stay high because it's a flip-flop. When this gets about 2/3, it'll then trigger the reset stage and come back down. So it's got to go through 2 of those 1/3 chunks, hence why the natural log of 2. Like I said, 2 of those units off. Does that make sense? Yay. Right? So that's basically the whole thing. That is that first equation. It's pretty direct from here. The second, right, this gets high enough that it resets it. The output goes to 0. This goes to 0. Right? That's my discharge line. Hooks me to ground. And then this capacitor will discharge through R2 to ground. That means that to go when I'm low, how long does it take for this to discharge back down? Right, so it gets to the 1/3. Well, it's got to go, if it was above 2/3 before, it's got to then go down to below 1/3. So it's got to go through at least 2 of those units again. That's another natural log of 2. But it's discharging through R2. R1 is not involved. So this is how you can set the difference in the duty cycle. The duty cycle is just time high over time high plus time low. If you shove them in and cancel stuff, you just end up with this. Now, if you notice, typically R2 tends to be big. So this is going to get closer and closer to that 50% mark. And depending on how these go, it'll change the duty cycle off there. But that duty cycle is always going to be over 50% under this configuration. It'll be very stable, it'll be nice and clean, all kinds of stuff, but it's at least 50%. If you want less than 50%, what we do is we hook in parallel with resistor 2 a diode pointing down. Okay? Now, when that happens, when I'm in the charging mode, right, it goes R1 and it goes through the very fast diode, bypassing R2, so this charges based on R1 only. And when it goes to discharge, it's reverse biased the diode, so the diode is essentially removed, so it still discharges through R2. So the equations then become there. And now by selecting, it becomes basically R1 over R1 plus R2. And now you can pick that ratio to get less than. So that's how you can get larger duty cycles. But you notice on this one, they set it with just the high only. Do we feel good with this? Okay. Do we all feel comfortable why this is set up? Okay. This one I didn't correct because I thought that chart was quite accurate for this one. I thought this one was better than the table when I found the table. Because time-wise, this one's easier. The other one had 2 times, so it was just kind of unclear. This is a single time, much nicer. All right, if you look at it, it looks very similar. Again, 4 and 8, 1 and 5, we're still going down to that 10th right? My output here, right, from 3, standard stuff, you still have the resistor between our power line and 7, my discharge. But now 7 and 6 are hooked to, 2 is not hooked together. Notice there's a little gap there telling you it's running independently. So the threshold is now my input for this one. Right? So you give it the boop, I want to go. So that's my input. When my input is high, it does nothing. I give it a drop. Whenever that drops, it turns things on. Right? So it doesn't matter how long this stays dropped, it converts it over, and then we just start our timing. From then on, right? It's high, so I'm going to charge this, so it just charges through R. We don't need the other resistor because we don't want the other one to come back up again after a point. We want that one just controlled by you. So we just remove 2 and its associated resistor and we're done. It's essentially the same circle with that modification made. And it just allows you send the signal, you get this, and this, the time period it stays up is determined by here. So again, now we don't have the 2 periods that's going on, so you got to go further. You're going from ground all the way up to nearly full charge. So, but it's just an R and a C. Yay! All right. This is nice in that you can look at the resistors and you can see the time, right? That's in right here up to 10 seconds down to 10 to the minus 5th seconds. And you can just look, you kind of pick your resistor to get so that whatever you want is fairly safely on here. And then you go, okay, let's say I want to pick the 100K and I want it at 1 second. I can say, okay, 100K is here. There's my 1 second. So I need a 10 microfarad capacitor. And just let you pick all the components to build the circuit. Make sense? Yeah, so it's pretty easy design too once you understand it. Here's bistable, our last one. This one's really simple. It's just 2 triggers to it. All right. So you have a trigger and a reset. Hook to the trigger, hook my reset area. You connect them. That's just for current buffering. So when I push the button, it grounds it. All right. When I ground it, if I ground reset, it does a reset. If I ground trigger, it triggers a set. If I push them both, who wins? Reset. Reset always wins. It's asynchronous. Right? You see our same little capacitor removing noise. Yeah. Otherwise, we're good. 7, remember, is an output. Okay? And we are not doing anything basically with our 6 to turn it back off. Right? I don't need a threshold to turn it off. I'm turning it off by the reset. This one's easy. There's no timing. It's when you push the button. This one right here, some people call Schmidt trigger mode. It's not. So actually, the one I stole these graphics from was calling this Schmidt trigger mode also as a second name. That's not true. This is Schmidt trigger mode. Who knows? It doesn't exactly look the same. Right? And the reason is I don't want 2 inputs coming in. Schmidt trigger mode is supposed to work off a single system and basically debounce it in both directions. So essentially on this one, I've got my capacitor on my input, right? And that's hooked to where my threshold is. I got my reset on it. I've got my resistances. And depending on how you change this, right, it's basically going to get filtered through to your system, and you are going to charge or discharge out, depending on which resistor you're on, to charge it, pull it up or down. And that does your timing off of them. Now, there's a lot of similarities. If you look at the output, if you were to split the highs and lows into those two button pushes, it would be exactly this. And if you hook those appropriately together, it will look like this. Right? Because this is now my switch. And I've basically taken those two and wrapped them around and just hooked the resistor for safety on both sides. But other than that, it's basically the same thing. But it's got to only have a single input. So they are related, they're just not the same. Other fun things, you can take square waves and make triangle waves. You can make all kinds. So you can also do this as function generators. Since it can be used to generate a phase lock loop, you can make, frequency dividers and all kinds of other fun stuff with this too. There's a lot of different things you can build with these lovely 555 timers. So here's my circuit that I want to build. All right, here's your 555. I put it in the same basic area, 8415. All right. Here's my trigger, right, and my my threshold. And then I just have a capacitor between these two and discharge. I have resistors that have been switchable. And then a resistor between discharge and power. That's our important part. Which system am I using? So how many agree bistable? It looks much like bistable, right? Because I got two switches. And ask yourself the question, is one the same? So do yourself a favor, ignore one of my two switches. Because if you're not push buttoning, it's disconnected. So imagine I'm only pushing one button at a time. What does it look like? So if I'm pushing this one here, just as a button, right? What does the circuit look like? You got a resistor between power and 7. You've got a resistor between 7 and 6-2 group. And then you have a capacitor to ground. What's that? It's astable. You have two different astables. This is going to send a repeated pattern of one of two things. By choosing these resistors, you're choosing the duty cycle. The duty cycle is the code you're sending. So I picked the ratio to say, go to one end, go to the other end. That make sense? And there it is. Now you notice I picked one really small here because that also lets me go into the low end of things without too much trouble. This right here, the capacitor, basically sets my timeline. So you'll see that's your first choice. Then the resistor range will set it. So, by picking this one, I'm dealing with somewhere in the hundreds of times a second, 1,000, somewhere in that zone. So you can see if you look up 100 nano. Oops. All right. 100 nanofarads. I'm right around 100 hertz. And depending on how I pick these ratios, it'll adjust that a little. Right? But then depending on how I pick my ratios here, will set what that duty cycle is. And we're picking this one we bump up to 33, right? So when we look at this, we've got 33 plus in the 60s, so that's somewhere in the hundreds, plus 168, 170, somewhere in there. Right? So you have 100 over about 170. And then for the other one, we cut this one to 10. Okay. So then I get 33 plus 10 over 33 plus basically our 20. So then I've got, 33 over 50. So that's kind of my two ranges that I'm jumping between on the signals, right, which will determine our duty cycle, i.e. position. Make sense? And the output, this one shows it as square, but it's not square. Okay. If we're good with this, I believe that was my last. That's this one. Just as a note, right? You can see I'm driving and I'm driving a NPN switching ground. Right? So the N1s always switch ground. This is my signal. That's my three positions. Red wire, black wire, and this is either white or yellow, depending on the particular servo you buy. Either one means control wire. And then these are the other configuration ones I've got. All right, if we feel good with that, I'm gonna switch over and let you see, because that's, I believe, yes, the last slide. Oops. I'm not sure if I can make this really big or not. Or small enough if you want, you can, you're welcome to come up. I'm not sure how I can make this completely big to everybody, but there's only like 3 of you. So, okay. So this is essentially, I'll pull the controls out a little bit prettier for all of you, but you can kind of see there's our laser diode. I initially put on this rather fancy paper clip to adjust where its position is. Let me see if I can prop this back end up a little bit just so you can see it kind of hit the. Now you can see it hitting the base. All right, so that's kind of where we're going to be rotating on. And then we've got 2 button controls on this. All right, one goes reverse and one goes forward. See, it goes all the way to the stop, and you have to reset them. That gives you an idea about how fast it moves. Now, if we want to slow this down, it will slow down a little bit because this isn't super powerful. Once we put something on top of it, it's going to have to move the mass, so it will slow down. So I tried to set it a little bit fast here so that once we actually had a load on it, it kind of moved at a reasonable pace. If we want to adjust the speed, we adjust the capacitor. And we could just swap that capacitor out for a different size one, and we can make it faster or slower as needed. If a servo doesn't get there as fast as it wants, it has feedback, so it recognizes it's not there, and it keeps applying it until it gets there. So that's why this is reasonable. So just switching between the 2 sides for us. So that's basically our system and how we're going to operate. I'm going to put a mounting, like I said, a little plate on top of that. Pretty easy to do. That's what these are. I'm going to turn this off. And unplug. So this will be set up with probably this round one, and then I'll attach a little plate on top of it, and we can put on most likely the system we had that had the little porcelain or otherwise little BBs in there. If you remember, we did for the ultrasound. It's about the right for the light to go through. You've already used it once, so you have a little familiarity with it. And the chapter I'm going to send you, it specifically talks about dispersion, and it does all of its work around spherical targets. So that's not an accident. That's why I picked the spherical targets for what's in there, so it would match the chapter I was going to share with you. But essentially over Thanksgiving, you can then just kind of read up on that, and we can talk about it when you get back. I am not planning on doing a big lecture on that. My plan is to kind of discuss with you the ideas that are on, so you understand them. Again, you don't necessarily need to be perfect on all that math, but it's helpful to kind of know where things are and how they correspond and what coefficients you're finding. When you try to solve things, if you understand the equations, you're better off. If anybody wants to try it now, you are more than welcome to. I'm happy to plug it back in and let you play with your heart's content for it, just to see you get the use of it. Again, I did left for reverse, right for forward. And I picked that because it was forward towards where the laser is. So I was just going in the direction the laser was pointing as forward. It's off right now because I got that little switch.
Okay.
So you don't drain the battery. Now it's on.
Sweet.
All right, so you can
Nice.
see it does a fairly decent job. You can see it goes through my finger pretty well.
Mhm.
Yeah. So it'll be plenty good for what we're dealing with on. Right. So it'll give us a good amount of penetration with it. Yeah. And once we put this on the outside of a box, I can just tape the paper clip to it. Joy of paper clips. But if anybody wants to try the buttons, you are welcome to play with it for the servo driver. You can see the basic setup is exactly what we talked about before. And again, it's just kind of a nice, another nice application of a 555, which, like I said, once you start thinking about how many things have to do with basic timing and flipping between some states, you want more states, you can always get multiple timers and flip between and use one timer to trigger other timers to get different speeds of systems. So it's very easy to get more life scale ones. People have scaled these systems by picking larger capacitors to go up to 15 minutes. When you get much beyond 15 minutes, the electrolytic capacitors they have nonlinear charging, so it can mess your timing up. It charges faster at the beginning, and as it gets full, electrolytics kind of slow down at their rate. They can slow down as much as a third. So if you're doing electrolytics, you don't want to go all the way to full charge to be able to drive it. But other than that, you're good. Any questions? Okay, I'm going to stop the video if you